So I had some problems with the recording from the lecture on Wednesday last week, so I'm going to repeat a little bit of what I did then. And also this is a kind of review. So of what we did last week. There were 3 remaining sections in this chapter to cover. And the first is implicit differentiation, which is a kind of application of the chain rule. So you might have some curve given by an equation like sine x plus sine y equals y. So you can think of this as a curve. Whatever it looks like, it's all the points in the plane that satisfy this equation. And on any point in the plane, there is likely a derivative, there's likely a tangent to the curve, and we want to be able to find the slope of the tangent or the derivative. We want to find dy dx. So here we have sine of x. Here, this is the sine of y, but y is a function of x. So we take this expression and we differentiate. The derivative with respect to x of sine x plus sine y, that's the derivative of sine x with respect to x, plus the derivative of sine of y with respect to x. This is equal to, what's the derivative of sine x with respect to x? That's cosine x. The derivative of sine y with respect to x by the chain rule is the derivative of sine y with respect to y times dy dx. So this is cosine x plus the derivative of sine y with respect to y is the cosine of y times dy dx. So this is the derivative of the left-hand side of the equation, which is the same as the derivative of the right-hand side of the equation. So we get this expression that involves dy dx. We can solve for dy dx. We get that we bring this term over to this side, dy dx minus cosine of y dy dx, which is 1 minus cosine y times dy dx equals cosine x. So dy dx, that's what we want to solve for, is cosine x over 1 minus cosine y. And that's the answer. At any point on this curve, the derivative at the point xy is given by this expression. So that's an example of implicit differentiation. Let me do another example, because this is an important technique. Suppose we have a curve given by the equation 6x cubed plus 7y cubed equals 13xy. So we want to find dy dx. So if you differentiate with respect to x, the derivative of 6x cubed is 6 times the derivative of x cubed, which is 3x squared. The derivative of 7y cubed with respect to x is 7 times the derivative of y cubed with respect to y times dy dx equals the derivative of 13xy. By the product rule, that's the derivative of 13x, which is 13 times y, plus 13x times the derivative of y with respect to x. So we have 2 terms that involve dy dx. I bring this term over to this side. I have 13x minus, this is 21y squared, dy dx equals 6 times 13, 18x squared minus 13y. So dy dx is 18x squared minus 13y over 13x minus 21y squared. And that is a nice example of implicit differentiation. Okay. And this is very useful for finding derivatives of, for example, the logarithm and the inverse trig functions. So if we let y equals the log of x, the natural log of x, we want to find dy dx. Well, what we know is the log and the exponential are inverse functions of each other. If you take e to the log of x, you get x for all x greater than 0, which is where the log of x is defined. So actually, here I'm just using the chain rule. So the derivative of x with respect to x is the derivative with respect to x of e to the log x. The derivative of x with respect to x is 1. The derivative of e to the log x is, by the chain rule, the derivative with respect to x of the log of x times e to the log x. Again, e to the log x is x, so this is x times the derivative of log x with respect to x is equal to 1. So if you divide, you get the derivative of log x with respect to x is 1 over x. That's one of the basic derivatives you have to know. Similarly, you can get the derivatives of powers of x. So suppose we have the general exponential function. You take a number b greater than 0, and you write y equals b to the power x. So we already know the derivative with respect to x of e to the x is e to the x. That's one of the most fundamental differentiation formulas. But what about when you're taking not e to the power x, but b to the power x? So you can write b as e to the log b. That's the definition of the logarithm. So b to the x is e to the log b to the x, which is e to the log b times x. So dy dx, by the chain rule, you take the derivative of log b times x with respect to x, that's log b, times the derivative of e to the log bx times e to the log bx, or b to the x. So this is the basic rule for the derivative of an exponential function b to the x. The derivative of b to the x, it's not b to the x in general, it's log of b times b to the x. So the derivative of 2 to the x is log 2 times 2 to the x. Any questions about these? And we can now use a technique called logarithmic differentiation to differentiate somewhat complicated rational functions. So this is called logarithmic differentiation. So suppose we have an expression like f of x equals x cubed minus 1 to the 4th square root of 3x minus 1 over x squared plus 4, and we want to find f prime of x. Now, we could use the quotient rule and the product rule and the chain rule, and we would solve the problem. There'd be a lot of calculation, but we could solve the problem. But an easier thing to do when you have something which looks at this general form is to take the log of f of x. So that's the log of this x cubed minus 1 to the 4th square root of 3x minus 1 over x squared plus 4. And we recall some of the basic rules about logarithms, that the log of AB is log A plus log B. The log of A to the power K is K log A. The log of A over B is log A minus log B. So those rules of the logarithm you learned about in pre-calculus and we use constantly. So first of all, here I have the log of a quotient. So let me just do this step by step. The numerator is x cubed minus 1 to the 4th square root of 3x minus 1 minus the log of the denominator, the log of x squared plus 4. And this is a product. So this is the log of x cubed minus 1 to the 4th plus the log of 3x minus 1 to the square root, which is the same as power a half, minus the log of x squared plus 4. So this is 4 times the log of x cubed minus 1 plus a half times the log of 3x minus 1 minus the log of x squared plus 4. That's all equal to the log of f of x. So now if I differentiate with respect to x by the chain rule, on the left-hand side, the log of f of x is 1 over f of x times f prime of x equals what? 4. What's the log of x cubed minus 1? It's 3x squared over x cubed minus 1 plus a half. What's the log? What's the derivative of the log of 3x? It's 3 over 3x minus 1 minus the log of x squared plus 4, which is 2x over x squared plus 4. So f prime of x is equal to the original function, f of x, times this expression, 12x squared over x cubed minus 1 plus 3 over 2, 3x minus 1 minus 2x over x squared plus 4. And if I put in what f of x is equal to and multiply across, it simplifies a little bit. And in any case, we get the answer. We can also get from implicit differentiation the derivatives of the inverse trig functions. So suppose y is the inverse sine of x. That's the same as saying x is the sine of y. So if we differentiate, the derivative of x with respect to x is the derivative of sine y with respect to x, which is the derivative of sine y with respect to y, dy dx. That's what we want to know. That's cosine y, dy dx, and dx with respect to x is 1. So that says dy dx is 1 over cosine y. But of course, we would like to have everything in terms of x. But we always know the basic trig identity, sine squared y plus cosine squared y equals 1 for every angle y. Sine y is x, so x squared plus cosine squared y equals y. Cosine squared y is 1 minus x squared, so cosine y is the square root of 1 minus x squared. So this is 1 over the square root of 1 minus x squared. So that's the derivative of the inverse sine. And then we just work out the derivative of the inverse tangent. Y is the inverse tangent of x. So x is the tangent of y. So the derivative of x with respect to x is the derivative of tangent y with respect to x. The derivative of tangent y with respect to y is secant squared y, dy dx, that's what we get on this side, equals 1, which is 1 over cosine squared y, dy dx. So dy dx is equal to cosine squared y. If y is the inverse tangent of x, x is the tangent of y, the derivative of x with respect to x is 1. The derivative of the tangent of y with respect to y is secant squared y, which is 1 over cosine squared y. So when we differentiate this with respect to x, we get secant squared y dy dx. So dy dx is cosine squared y. How is that related to the tangent of y? I want to try to get everything in terms of x. So again, we have the trigonometric identity, sine squared y plus cosine squared y equals 1. If you divide by cosine squared y, this is tangent squared y plus 1 is 1 over cosine squared y. And tangent squared y, tangent of y is x. So this is x squared plus 1 is 1 over the cosine squared of y. So the cosine squared of y is the reciprocal of this. It's 1 over x squared plus 1. So that's the derivative of the inverse tangent of x. Okay. So now we can differentiate basically any function we're going to come across in calculus. And I posted just before class started today a review sheet of sorts for the midterm exam, which is next Wednesday, a week from Wednesday. And the largest part is just a series of functions you have to differentiate. The final section in this chapter, which is in some ways the most interesting, is the subject of related rates. So we want to use calculus to solve interesting problems, or not everyone finds them interesting, but at least to solve problems. So here's a classical type of problem. You have a building and a ladder. So this is a building, and that's a ladder leaning against the building. And the length of the ladder is 13 feet long. And someone starts pulling the ladder. They take the base of the ladder and they're pulling the base of the ladder away from the wall. So what happens to when you start to pull away the ladder? It falls down, leaning against the wall. So as the base gets pulled out, the top of the ladder is dropping. And the question is, so let's say that the base of the ladder is at the point X, and you're pulling the ladder out at a rate of 6 inches or half a foot per second. So the position of the base, which is X, dx dt, is increasing at a rate of 0.5 feet per second, right? So every second you pull this ladder 6 inches or half a foot to the right. And let's say the height of the ladder is Y. So what is happening to the top of the ladder as you pull out the base? It's dropping. So whatever dy dt is, it's decreasing. So the derivative is negative. And the problem is to find out how fast the top of the ladder drops when the base of the ladder is at position X, exactly 5 feet from the wall. So you have this 13-foot ladder. If the base is 5 feet from the wall, the top of the ladder is exactly 12 feet high, because this is a right triangle, and by the Pythagorean theorem, 5 squared plus 12 squared is 25 plus 144 is 169 is 13 squared. So when the base of the ladder is 5 feet from the wall, the top of the ladder is 12 feet high, but it still is falling down. So if you're standing at the top of the ladder, you might want to know, how fast are you falling? So the problem is, we know dx dt, we want to find dy dt. But we have a relationship between them. X and Y are related. They're related because this is a right triangle. And by the Pythagorean theorem, the square of this plus the square of this equals the square of this. So this side of the triangle is X, so that's X squared. The height is Y, so that's Y squared. And that's equal to the hypotenuse squared, 13, which is 169. So we have this relationship between X and Y. By implicit differentiation, if we differentiate with respect to t, so the derivative with respect to t of x squared plus y squared is equal to the derivative of x squared with respect to x, 2x times dx dt, plus the derivative of y squared with respect to y, 2y dy dt, and that's the derivative of this constant function, and derivative of a constant is 0. So this says if you solve for dy dt, 2y dy dt is minus 2x dx dt. The 2's cancel, and dx dt, we're told, is 5. So this is equal to minus 5x. So y dy dt is minus 5x. So dy dt is minus 5 x over y for any values of x and y. And when x is equal to 5, y is equal to 12. So dy dt will be minus 5 times x, which is 5, over y times 12. So this is minus 25 over 12 feet per second. So at the point when you are on the ladder 12 feet high, you're falling at a rate of 2 1/12 feet per second, minus 25 over 12 feet per second. So this is a problem about related rates. Any questions about this? So related rate problems are interesting because you're given a problem. It's usually a paragraph, it's words, and you have to understand, figure out how to translate the words into mathematics. All right, let's look at some more problems. We'll start with some geometrical problems. Suppose we have a square whose side is x. And the square is increasing, getting bigger. We're increasing the side of the square at a rate dx dt equals 2 meters per second. So every second, the square gets bigger and bigger and bigger. And as the square increases, the area increases. So the problem is at what, so this is the rate of increase of the side of the square. At what rate is the area increasing? Because when the sides get bigger, the area gets bigger. When the length of the side is 10 meters long. So we have to find a relationship between the area and the side. So let's say the area is A and the side is X. Well, we know area is X squared. And these are both increasing as functions of t. So dA dt is derivative with respect to t of x squared, which is 2x dx dt. And we're told dx dt is 2. So this is 2x times 2, that's 4x meters squared per second. So when x equals 10 meters, the rate of change of the area is 4 times 10, or 40 square meters per second. When x equals 20 meters, how fast is the area changing? This is when x equals 10. The area is increasing at 40 square meters per second. When x equals 20, dA dt is 4 times 20, or 80 square meters per second. So the bigger the square, the faster the area is increasing if the side is increasing at a constant rate. You can actually see that from a rough sketch. That is, suppose here you have your square and you increase the area by a little bit. So the added area you get, the increase in the area, is this. If you have a bigger square and you increase the area, the side, by the same amount, the added area you get is this. And you can see here, the red amount of new area is much smaller than here, where this red amount of new area. So even though the side of the square increases at a constant rate, the area increases faster and faster. Any questions about this? I think it's a lot of fun, so we'll keep doing problems. I'm doing some problems at the end of the section on related rates. This is problem number 22. Two boats leave a port at the same time. One of them is traveling west at 20 miles an hour. So this is a horizontal change. So say dx dt is 20 miles per hour. And the other is traveling south at a rate, let's call this dy dt, at 15 miles per hour. So this boat is going 20 miles an hour west, and this boat is going 20 miles an hour south. And if we look at the distance between them at any given point, that's this red line. And at some later point, maybe this guy is here, and this guy's over there, and the distance between them is this red line at a later time. And you see the red line gets bigger. So the rate at which the distance between them is changing is increasing. This distance from one boat to the other at any given time is getting bigger and bigger and bigger. So let's call this something. Maybe I'll just call this, say, D for distance. And the problem is find, let's not call it D, let's call it R. I'll call it Z. Find dz dt. Z is the distance between the two boats at any given time. So the first question is, after 30 minutes, how far is each boat from the port? Well, after 30 minutes, if the boat is traveling west at 20 miles an hour, it's moved 10 miles after 30 minutes. If the second boat is traveling south at 15 miles an hour, after 30 minutes, it's traveled half that distance, 7.5 miles. So after 30 minutes, the first boat is 10 miles west of the port. The second boat is 7.5 miles south of the port. At that time, how fast is this distance z changing? So again, if we let x be the distance of the first boat from the port and y the distance of the second boat from the port, by the Pythagorean theorem, we get z squared is x squared plus y squared. So if we differentiate with respect to t, the derivative of z squared with respect to t is 2z dz dt. And that's equal to the derivative of the right-hand side with respect to t, which is 2x dx dt plus 2y dy dt. And we can divide by 2, get rid of the 2's. So we have this equation. And so z dz dt is x dy dt plus y x dx dt and y dy dt for any x and y. But dx dt we know is 20. So this is 20x. And dy dt is 7.5. Sorry. Dy dt is 15 plus 15y. So dz dt is going to be 20x plus 15y over z. And after 30 minutes, the first boat is 10 miles west. That's 20 times 10. And the second boat is 7.5 miles south, 15 over 2, divided by this distance. What is this distance? So z squared is 10 squared plus 7.5. I'll just use fractions, 15 over 2 squared. So this is 100. 15 over 2 is 225 over 4. So this is 100 plus 225 is 625 over 4. That's z squared. So z is the square root of 625 over 4, which by a miracle is exactly 25 over 2. So we're dividing by z, which is 25 over 2. So we get 200 plus 225 over 2 over 25 over 2. So it's this times 2. So this is equal to 400 plus 225, 625 over 25. And 625 over 25 happens to be exactly 25. So the numbers cancel very nicely. And so when we have a boat traveling west at 20 miles an hour and a second boat traveling south at 15 miles an hour, the distance between them is increasing. And after 30 minutes, the distance between the boats is increasing at a rate of 25 miles an hour. Okay, any questions about this? All right. I'm just going to keep doing problems because they're interesting, and this is a very important technique to learn. Suppose we have an isosceles triangle. So an isosceles triangle is a triangle with two sides have the same length. And these are the legs, and this is the base. So suppose just to give these things names, suppose I call X the length of the two equal sides of the triangle, and B the base. And we're told that the legs are getting bigger at a rate of 2 meters per second. At what rate is the area? Oh, I'm sorry. This is an isosceles triangle, but this problem says an isosceles right triangle. That makes it a lot easier. So still a triangle where two sides have the same length. Say this is X and this is X, but this is a right angle. So we have this isosceles right triangle. And again, the legs are increasing at a rate of 2 meters per second. We want to find the area of the triangle. What's the area of the triangle? Area of a triangle is a half the base times the height. So X times that, half X squared. And we want to find dA dt when X is equal to 2 meters, when each leg is 2 meters long. So if we differentiate this with respect to t, we get dA dt is 1/2 2x dx dt. A half times 2 is 1. So that's just x, and dx dt is 2. So dA dt is simply 2x square meters per second. So when x equals 2, dA dt is 2 times 2, or 4 meters per second. So if you have an isosceles right triangle, the legs are increasing at a rate of 2 meters a second. When each leg is 2 meters long, the area is increasing at 4 square meters per second. Suppose I call this hypotenuse, no, I'll call it Z, why not? Find dA dt, the rate at which the area is changing, when Z is equal to 1. So when the hypotenuse of the triangle is 1 meter long, how rapidly is the rate increasing? Well, when Z is 1, I know what X is, because by the Pythagorean theorem, X squared plus X squared, or 2X squared, equals Z squared. So when Z is equal to 1, 2x squared equals 1, x squared is a half, or x is 1 over the square root of 2. And when x is a half the square root of 2, dA dt, which is 2x, is 2 times 1 over root 2, or root 2 square meters per second. And suppose we want to find the rate at which the hypotenuse Z is changing. We want to find dZ dt when the leg of the triangle is increasing at a rate of 2 meters per second. Well, again, we have 2x squared equals Z squared. So 2 times 2x dx dt is 2z dz dt. And dx dt is 2. So this is 2 times 2 times 2. 8x is 2z dz dt. At what rate is the hypotenuse changing? What is dz dt? dz dt is 8x over 2z, which is 4x over z, but z is square root of 2 times x. is 2 root 2. So when x is increasing at a rate of 2 meters a second, the hypotenuse is increasing at a rate of 2 root 2 meters per second. Any questions about this? These are really problems you need to think about, usually quite a bit. Okay. Let's look at some more problems. Suppose we have the parabola y equals x squared. And we have a bug moving along the parabola, where for this bug, so this is a bug on the parabola. And the distance d of that bug, or I call it z, the distance from that bug to the origin is increasing at a rate of 1 centimeter per second. So dz dt is 1 centimeter per second. Sorry, just to use the same dimensions of the book, 1 centimeter per minute. So this bug is crawling very slowly along, and every minute it's only moved a centimeter, but that's just what it is. And we want to find how fast the x-coordinate of the bug is changing, dx dt, when the bug is at the point on the parabola xy equal to 2 comma 4, right? When x is 2, x squared equals y is 4. So at the point 2, 4, we want to know, so this bug is still moving along, so it's such a way that its distance to the origin increases at a constant rate of 1 centimeter per minute. And how fast is the x component of the bug increasing at 2, 4? So what can we say? What is z in terms of x? So our picture looks like this. This is x, this is y, this is z. This point on the parabola is xy squared, is at y equals x squared, is x comma x squared. So this point on the parabola, xy, is really x comma x squared when y equals x squared. So we have a right triangle. This distance is x. The height is x squared. What is z? So let me just draw this picture again. This is x squared, this is z. By the Pythagorean theorem, z squared is x squared plus x squared squared, or x squared plus x to the 4th. So 2z dz dt is 2x dx dt plus 4x cubed dx dt. right? If z squared is x squared plus x to the fourth, 2z dz dt is 2x dx dt plus 4x cubed dx dt. And dx dt is, and sorry, dz dt, we're told, that's what we're given. The rate of the distance of the bug from the origin is 1. So this dzt is, this is just 2z. So if I can divide by 2, I get z equals, and I can factor out dx dt times x plus 2x cubed. So the rate at which the x-coordinate of the bug is changing is equal to z over x plus 2x cubed. And when x is 2 and y is 4, 2, 4, this is the square root of 2 squared plus 4 squared, which is the square root of 20, which is 2 root 5. So z is 2 root 5, x is 2, plus 2x cubed is 2 times 8, plus 16. So that's 2 root 5 over 18, or root 5 over 9. So if I did the arithmetic correctly, if a bug is crawling up a parabola in such a way that its rate, its distance to the origin is increasing at a rate of 1 centimeter per minute, then when it is at the point 2,4 on the parabola, the distance, it's the x component of the position of the bug is increasing at a rate of root 5 over 4 centimeters per minute. All right, well, let's keep trying to solve problems. Right? So this is going to be the following. So this is number 31. So we have a water heater, a water tank, if you like, which is a cylinder which has a radius r equal to 1 and a height h equal to 4. And I will remind you, if you have a circular tank of radius r and height h, the volume is pi r squared, the area of the cross section, times the height. So the volume of a right circular tank of radius r and height h is pi r squared h. Okay. And the tank is being drained. And so we're draining the tank. And the water level, the height, is dropping at a constant rate. So let's say this is the tank, but the water is just going up to there. And the water level, the height, is y. And we're told that the water level is dropping at a rate dy dt, it has to be negative, of 6 inches per minute. Find, so this is the height at time t. We have the volume of the water. Find the rate at which the volume is decreasing. I should say dy dt is minus 6 inches per minute because the height is dropping. And we want to find dv dt in cubic feet per minute. Okay. So this is the way problem 31 is stated. A water heater has the shape of a right cylindrical tank with a radius of 1 foot and a height of 4 feet. It's being drained. How fast is water draining out of the tank in cubic feet per minute if the water level is dropping at 6 inches per minute? And you'll notice, first off, that we have different units of length and volume. Here, this is in inches. Here, this is in feet. We have to make sure we have the same units in both. So 6 inches per minute is the same as a half foot per minute. So in terms of units of feet, square feet, cubic feet, the height of the water level is dropping at a half a foot per minute, and we want to find how fast the volume is decreasing in cubic feet per minute. So we have a relationship between the volume and the height. In general, the volume is pi r squared h. If r is equal to 1, the volume is simply pi times h. So dv dt is pi times dh dt. Sorry, the height, h, let me just call this h, dh dt. dh dt is minus a half. This is minus a half pi cubic feet per minute. That's all there is to it. If we want to try to understand this perhaps a little bit better, here we have our tank. And in 1 minute, the height of the water drops a half a foot. So the amount of water that drained out in a minute is the volume of a right cylindrical cone whose height is a half and whose radius is 1. And the volume of this cone, pi r squared h, r is 1 and h is a half, it's just pi over 2. So every minute you lose pi over 2 cubic feet. That explains this answer very nicely. Any questions about any of these? Let me do another couple of problems and then we'll be done for the morning. This is problem number 43. There's a street, and on the street, 20 feet high, is a street light. And there's a 5-foot woman standing here. And so the light casts a shadow, right? The light comes down and right there is the shadow. That's the part. I mean, all of the street is illuminated except the part that this woman's body blocks. So this body is 5 feet tall, and here is a shadow. But this woman isn't standing still. She's walking towards the street light. Let's say the distance from the street light is x. So dx dt is decreasing at a rate of 8 feet per second. And as she gets closer to the wall, like when she's here, now this is her shadow. Her shadow is smaller. So as she gets closer and closer to the street lamp, her shadow is decreasing. And that's called the length of the shadow L. We want to find dl dt when the woman is 15 feet from the wall. Okay. So I have to find a relationship between the position of the woman and the length of her shadow. So this is a little bit of geometry. Let me draw this picture again. So here's the street lamp. Here's the woman who's 5 feet tall, and she's X distance from the street light. And this light from the street light comes down like this in a straight line. And this is the shadow, call this L. So what is the relationship between the shadow and the position of the woman? So one thing we can say is, this is a right angle, this is a right angle, and this big triangle, this big right triangle, and the small right triangle share this acute angle. So these triangles are similar. So the ratio of this to this is the same as the ratio of this to this. Right? So for similar triangles, you have the same ratios of the sides. So this side is 20, and this is L plus X. So 20 over L plus X. And in this triangle, the ratio of the sides, this is 5, so the woman is 5 feet tall, and this is L, equals 5 over L. So it seems that we can use this equation to relate X and L explicitly. If I cross multiply, 20L is 5L plus 8X. 5 into 20 is 4. So this says 40L is L plus X, or 4L. So 3L equals X. This is a relationship between X and L. So dx dt is 3L, 3 dl dt. And we're told this woman is walking at a rate of 8 feet per second. So dx dt is -8. So dl dt is -8/3. Right? 3L equals X. So dx dt is 3 dl dt, and dx dt is -8. So dl dt is -8/3 feet per second. So this is changing at a rate of -8/3 feet per second. So take a look at that for a little bit. So the length of the shadow is changing at -8/3 feet per second. At what rate is the tip of her shadow moving? So this is the length, but the tip at this position is L plus X. So the derivative with respect to time of L plus X is the derivative with respect to time of L plus the derivative with respect to time of X. She's walking at 8 feet per second. So this is -8/3 plus 8. 8/3 is, sorry, -8 feet per second. This is 24/3. 24 plus 8 is 32. So this is -32/3 feet per second. So the tip of the shadow is changing much faster than the length of the shadow. Let's do one more, and then we will stop for the day. But it's really important to spend a lot of time trying to understand how to do these problems. Let's look at the Navy problem. This is problem 61. So a boat leaves a port, here's the port, traveling due east at 12 miles per hour. So let's call this distance x, and dx dt is 12 miles per hour. At the same time, another boat leaves the same port traveling northeast. That's in this direction. Let me call this something. I'll just call it y, just to have some letter. And dy dt, traveling northeast, is their speed is 15 miles per hour. Right? To say this is traveling northeast and this is east means this is what you would call a 45-degree angle in high school and pi over 4 radians in college. So that's the angle. And I want to measure the angle, the following angle. So let me put this out of the way a little bit. So this dx dt is changing at 12 miles per hour, and dy dt is the speed of that boat is 15 miles an hour. So it's traveling faster. And if I draw, I want to find the angle between the boats at any given time. Where the angle I'm interested in is the following. I take the line joining the two boats, and I look at the vertical line here, and this is the angle I want to measure. So for this angle theta, I want to find the rate in radians that the angle is changing. So the question is, how can I describe theta somehow in terms of x and y? That's an interesting question. So if this angle is theta, this angle is pi over 2 minus theta, and this plus this add up to pi. So this angle is pi over 2 plus theta. Sorry, pi over 4 plus theta. So I want to find d theta dt. So I would love to express theta in terms of x and y, because I know x dx dt and dy dt. That's an interesting problem. If this angle is theta, Does it depend? Does it vary with X and Y? Let's look at an example. I'm curious about this. So after 1 hour, this is 12. This is 15. If this is 12, this is 12. This distance is 12 times the square root of 2, which is always bigger than 15. And if you go a greater time, let's say you go t hours, and this is 12t, and this is 15t. And this is this, and this is this. And this distance is 12 times the square root of 2t. So these triangles are always similar, and this angle is not going to change. So d theta dt will be 0. So there will be a constant angle between the movements of these two boats. And if this were a geometry class, we could spend a little bit more time looking at this, but it's really quite a pretty problem. But this angle doesn't change because at every point the triangles are similar. And the angles in a similar triangle are equal. So d theta dt is 0, theta is fixed. Okay, well, I encourage you on the Pearson MyLab website to do problems on related rates, because these will not be on our midterm exam, but they will definitely be on the final exam. So it's really worthwhile to think about it. Okay. Any questions about this? Again, I remind you, I posted review problems on Blackboard, and I emailed them to you, so everyone has it in your email inbox. We have problem sessions Monday, Wednesday, and Friday. There's one this evening at 7 o'clock. And again, I encourage you to log in and ask questions, because that is the best way to learn calculus and the best way to resolve any difficulties you might be having. Okay. All right, all. We are then done for the morning. Be well, stay warm. See you Wednesday.
Professor,
Yes,
I know you've been recording the sessions. Where can I go to rewatch them?
they're all on YouTube.
Oh, perfect. All right, thank you.
I mean, the information I posted on Blackboard at the beginning of the semester, it gives the YouTube channel and playlist.
Awesome. All right.
The
Thank you
only
for your
one
help.
that's not there is the last one. It somehow got screwed up somehow. So that's why I repeated today a lot
Okay.
of what I did on Wednesday of last week. The topics on the midterm, again, I wrote out an email to everyone, some advice, information about how to study calculus for the midterm and exactly what the midterm covers. So I already sent that out to you, and it's in your email file. I did that over the weekend.
Yeah, I actually printed it out.
Yeah. Okay. Any other questions? Anything else I can answer or help you with? Okay. All right, everyone. See you Wednesday. Bye.